Sorry about the delay. Let's now get started. Okay, so for this problem, the idea here is we want to expand our expressions here. Let's say y plus 4 is equal to x squared minus 4x plus 4. So from here, what we can do is we can subtract 4 from both sides to get that y is equal to x squared minus 4x. And then on the second equation here, we can subtract 4 from both sides to get that is equal to x is equal to y squared minus 4y. Okay, so now what can we do? So now what can we do? Well, from here, we can really see that we want to find x squared plus y squared. So from this expression, we know that x squared, we can add 4x to both sides to get x squared is equal to 4x plus y. And from here, we can get y squared is equal to x plus 4y, since you just add 4y to both sides. And that means x squared plus y squared is just going to be equal to 5x plus 5y, or 5 times x plus y. Now we really just need to find x plus y. So now what can we do? Well, what we can do is you can see that you have x squared term and a y squared term. So we can subtract the equations. So let's just do x squared minus y squared, because when we do that, we can see that it's relating to difference of squares. So when we subtract the equations, we get x squared minus y squared is going to be equal to, so x squared minus y squared will just be 4x plus y minus x plus 4y, which is going to be 3x minus 3y. Okay, so now what can we do? Well, from here, we'll see that x squared minus y squared can be factored. And we can factor x minus y times x plus y is equal to 3 times x minus y, because you can just factor it by difference of squares. And now we know that we can divide by x minus y, since x is not equal to y. We know x is not equal to y, meaning that if x is not y, then x minus y is not 0, right? Because x minus y will only be 0 if x is equal to y. And that means that we can divide by x minus y without having to worry about dividing by 0. So these terms will cancel, and we're left with x plus y equals 3, meaning that x squared plus y squared is 5 times x plus y, or 5 times 3, or 15, which is the answer for this problem. So this is a really clever problem in the way that the idea here was that when we have these equations together, we get that x squared plus y squared. So the tricky part of this problem is saying that why should I subtract the equations? You might be asking, why should I subtract them? Because an x squared term and a y squared term. And it just reminds us, we just look at some key patterns in our expressions to see that if we subtract them, what would happen? Can we rearrange anything? Can we get any information out of subtracting them? Because x squared minus y squared is something that we're familiar with. We know it factors into x minus y and x plus y. So that's why you think of doing this technique. Okay, so now let's move on to today's topic. So great job to everyone who attempted the homework from last week. Also, we will be having homework problems for this week as well. And it's really important that you do the homework problems, because even besides just attending the class, you need a lot of practice in order to do well on the AMC 1012. So the homework problems are 5 problems that are related to the topic, so you can get some practice with the techniques that are taught in the class. So I highly recommend you to try the homework problems and just attempt them. Maybe you don't solve many of the problems, but it's still good just to attempt the problems. So now let's just do a quick review of the formulas we learned from the AMC 8 classes. And factorial is just n times n minus 1 times n minus 2 till 1. And number of ways in a line is n factorial. In a circle, n objects in a circle is n minus 1 factorial. And then word rearrangements, we just do n factorial over the d1s, d2s factorial. And we already learned these concepts in the AMC 8 classes. So check out, you can review those videos for more details and information. We also have permutations and we also have casework, which is by considering different cases, and overcounting by subtracting the bad cases. Basically, like subtracting the parts that do not belong from the cases. Okay, so now let's look at some arrangements problems from the AMC 10. We'll start off with some very simple problems from AMC 10, and we'll progress to some hard problems from AMC 10 and 12. So let's start off with some simple examples. Henry's Hamburger Haven offers its hamburgers with the following condiments: ketchup, mustard, mayonnaise, tomato, lettuce, and pickles, and cheese, and onions. Wow, that's a lot of condiments. So we have 1, 2, 3, 4, 5, 6, 7, 8 condiments. And then we can either have 1, 2, or 3, oops, that was a bad line, 1, 2, or 3 meat patties in any collection of condiments. How many different hamburgers can be ordered? Okay, so how can we solve this problem? We have 8 condiments and 3 different choices for patties. So I'll give you a minute or two to try this on your own. Okay, so this was a simple example that we started off with. Now let me go into the solution for this problem. So the idea here is that we have 8 different condiments. And for each of the condiments, we have 2 choices. We can either include the condiments or not have the condiments. So basically for each of these 8 condiments, so we have 8 of them, we can either choose to include the condiment or not include the condiment. So you can either choose to have ketchup or not have ketchup. So 2 choices for ketchup. We can either choose to have mustard or not have mustard. Have mayonnaise or not have mayonnaise. So overall, there's just going to be 2 to the power of 8 choices of whether we want to have each of the condiments. Because there's 2 choices for each of the condiments. Yes, have it, or no. And then we also have 3 choices for the meat patties. 1, 2, or 3. So let's multiply by 3. Because we can have 1 meat patty, 2 meat patties, or 3 meat patties. So overall, the answer is just 256 times 3, which is 768. And that's the answer for this problem. Okay, so now let's take a look at a basic word rearrangement problem. And this is mostly just a review from the AMC 8 classes, these problems. How many distinct arrangements of 1 brown tile, 1 purple tile, oops, getting cut off, 1 purple tile. I think I should make that a little bit smaller so it fits. Sorry if it was hiding the whole class. That should be better now. Okay, so one brown tile, so 1B, 1 purple tile, so a P, 2 green tiles, and 3 yellow tiles. So Y. So overall, we have 7 letters. So by the word rearrangement formula, how many ways can we arrange these 7 letters? Well, we have 7 letters, so 7 factorial, divided by, we have 3y, so 3 factorial, and then we have 2 factorial. And this is equal to 7 times 6 times 5 times 4 times 3 times 2, divided by 3 times 2 times 2. These 2 cancel, this term cancels. We're left with 7 times 5 times 4 times 3, which is equal to 7 times 60 or 420, which is the answer. So this is just a simple example to warm up. Now let's try a slightly more sophisticated example. So this time we want to form a tower with a height of 8 cubes, but we have 2 red cubes, 3 blue cubes, and 4 green cubes. And of course, 1 cube will be left out because now we have only a tower of 8 cubes when there are really 9 cubes that we have. So now, how many ways can we do this? I'll leave you to try it for a minute on your own before we go into the solution. And it's a very clever solution. Okay, so now let's go into the solution for this problem. This actually is a really clever solution, and we'll actually progressively get into some much harder problems towards the end. And those will be really clever applications of the technique that we know. So the idea here, since we have a tower of 8 cubes, and we actually have 9 cubes, we can just arrange them. Okay, so let's modify the problem. Let's say we want to form a tower with 9 cubes only, so 9 cubes. So let's just imagine it was instead 9 cubes instead of 8 cubes. Now, how many ways can we do this? Well, that just becomes arranging 2 red, 3 blue, and 4 green in a line. You can think of it as arranging the word with 2 R's, so RR, blue BBB, G, 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 G. And how many ways can we do this? And this is essentially the number of ways to have a 9 cube tower. By word rearrangement formula, 9 factorial over 4 factorial over 3 factorial over 2 factorial, which should be equal to 9 times 8 times 7 times 6 times 5 times 4 factorial over 4 factorial times 3 factorial times 2 factorial, which, what is that then equal to? Well, these terms will cancel, and these terms will cancel. And of course, 2 is just going to cancel with 8 to get 4. And we're left with just something that evaluates to 36 times 112. And that should be equal to 1260. Because it's going to be 4 times 35 times 9, which is 140 times 9, or 1260. So there's 1260 ways to arrange the 9 letters, but that's a 9 cube tower. Now we have the 8 cube tower. Now imagine we have a tower, but now the last cube is not there anymore. So now the last cube is not there anymore. Now what can we do? Well, we can imagine just taking the last cube and putting it off to the side. So basically what that means is that for any 9 cube tower, we can just remove the last block from the bottom and put it on the side, because then we have an 8 cube tower. And so the number of ways is just also going to be 1260. Because the number of ways of putting 8 cubes and 1 to the side is the same as putting 8 cubes on the top and 1 on the bottom. With a 9 cube tower, basically. So the number of 9 cube towers is the same as the number of 8 cube towers. Okay, so next problem here. A license plate has 4 digits and not necessarily distinct, and two letters. 6 characters may appear in any order, except that 2 letters must appear next to each other. How many distinct license plates are possible? So the idea here is that we have 6 total digits and letters. So 1, 2, 3, 4, 5, 6. So let's just say the 2 letters are, let's just say that the 2 letters are here. So let's say these 2 spots are both letters. Or let's say these 4 slots are digits and these 2 slots are letters. Of course, that's not the only case, but we'll worry about the other cases later. So then there's 26 choices for the letter, because there's 26 letters in the alphabet. And then 26 choices for the second letter here. And then there's also going to be equal to 10 choices for each of the 4 digits. Right? That's just direct counting. Right there. And this is just 26 squared times 10 to the 4. But then we also, not necessarily, let's say this is A and J. Maybe this is 9, 7, 1, 3. Just as an example. But now the A and J do not necessarily have to go in the first 2 slots. We can have, for example, if you have 6 slots, we can have the 2 letters go here. So we can have 2 letters can either go here. The 2 letters can either go here, 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 or here. For a total of 5 different possibilities where the letters can go. Because, for example, we can also have something like here, A and J here, and the digits at the other slots. So overall, there's going to just be equal to 5 different choices for where the 2 letters can go. So you just want to look at each of the pairs of slots. So it's going to just be, the answer is just going to be this. And that's the answer for this problem. Okay, so now let's take a look at our next problem. So now let's take a look at casework, which is basically just dividing into cases. So this is, I think, a really nice problem. So I'll give you some time to try and work on it on your own. And we're starting off with some simple examples, but we'll slowly get to some harder problems. Okay, so now let me go through the solution for this problem. So for this problem, basically the idea here is that we can look at different cases. So if the first letter is A, then the second letter can either be C or D. Right? Or let me just write it. So if the first letter is A, let's take different cases. First letter is A, B, C, or D. So if the first letter is A, then the second letter cannot be B because B is next to A alphabetically. So it can either be C or it can be D. And the other cases, but if it's C, then the next slot can either has to be B or D because those are the only two letters left. But then B or D, both of these cases don't work since B or D and both are both next to C alphabetically. And if it's A and D in the beginning, then the next letters can either be B or C, but then C is next to D alphabetically, so the next slot will have to be B. But then that means the last slot will have to be C, but B and C are next to each other alphabetically. So this case also won't work. And somebody mentioned, can you just do complementary counting? And you can do complementary counting, but I think it would be a little bit harder to do complementary counting than casework. But maybe there's also simple complementary counting solutions, so I'm sure that would also work. But I'm just going to show the casework solution. Okay, so and then another case is the beginning one is B. So if the first letter is B, then the second letter can either be A, C, or D, but it can't be A or C since that's next to B. So the next letter will have to be D because A and C are next to B alphabetically. But then if that's D, then this next slot has to either be A or C. But C is next to D alphabetically, so it's going to have to be A. And that means the last slot will have to be just going to be C. But then we see, yay, A and C are not next to each other alphabetically. So this case works. So for the next case, we can also have C. So if C is here, then, well, what are the possibilities for the second slot? The second slot can be A, B, or D. But it can't be B or D because B or D are next to C alphabetically. So it will have to be A. And then after that, what slot will it be? Well, it can either be B or D. But B is next to A alphabetically, meaning it will have to be D. And the last slot will have to be B. And we're good because D and B are not next to each other alphabetically. So another case there. And okay, so if the first letter is D, then the next letter can either be A, B, or C. But again, C doesn't work since it's next to D alphabetically. So it's going to be either A or B. Or let me write it in separate. DA or DB. These are the two cases for this case. So if it's DA, then the third slot will have to be either C or B. But then B is next to A alphabetically, so it's going to have to be C. And that means the last slot will have to be B. Uh-oh, C and B are next to each other alphabetically, meaning this case does not work. Now what about if it's D and B? Then that means the next slot can either be A or C. But C is next, A and C are both next to B alphabetically. So A or C, this case doesn't work. So we're left with just two cases as the answer. And that's the solution to this problem. Okay, so now let's take a look at our next problem. This is actually a little bit of a tricky casework problem. So I'll give you a couple minutes to try it out for yourself. Yeah, and this is a lot of casework. So I'll just give you a hint here. There's actually, when I first solved this problem, I did it in a very bashy way. I didn't do the most optimal solution. So I'm actually going to show you the quickest way of doing this problem, the fastest way. There's a much harder casework. When I first solved this problem, I just bashed it all out, all the different cases. But then there's the easier way, which I didn't know about, which basically is that I'll actually explain it later. So I'll give you time to work on it right now. Okay, so let me just give you a quick hint. So the idea here is that the only case that works is if you have 1A, 1, or I should probably define. Let's say that we have three different brother-sister pairs, A1, A2, B1, B2, and C1, C2. So I'll just give you a hint. The only case that works is if there's one A1, one B, and one C in the top row, and then there's one A, one B, and one C in the bottom row. This is the only thing that does work. And I'll explain the actual solution very shortly. So here's the hint again. There has to be one in the first row, and no other case works, and I'll show you why in a minute. But this is just a hint to get you started. Okay, so now let me go into the solution. So it's actually a very clever solution that I found out about. So basically, the cases are we can either have 1A, because remember, no two A's, or I didn't even explain the problem, so let me just explain the problem. Basically, we have three pairs of brothers and sisters from different families. They have to occupy the second and third rows. And each of them has 3 seats, and siblings cannot sit right next to each other in the same row or directly in front or behind, of course. So how many seating arrangements is what we want to find. Okay, so how can we do this problem? Well, the idea here is that the cases, like I said, this is the case that I work. It has to be 1A, 1B in the top, and 1A, 1B, C in the bottom. And this is one of the cases. So the idea here is that, we can just assume that there's one A1, B1, and C1 at the top. And of course, I'll multiply for the rearrangements later. So don't worry about rearranging. Okay, we can rearrange A, B, and C, and we can also switch A1, B1, A1, A1, A2, B1, B2, C1, C2. I'll account for that all at the end. Okay, so the idea here is, what we can try to do is, we can see that the different cases are A1, B1, C1. Let's say they're all top, at the very top. So that's one case where all of them are different. Both the A's are in different rows, both the B's are in different rows, and both the C's are in different rows. So something like I had earlier. And the other case that turns out doesn't actually work is if you have, let's say, two A1, A2 here. So firstly, let me explain why this second case at the bottom here doesn't work. So if you have, for example, two A1, A2 at the bottom, then this middle one in the very middle, let's say it's B1, I'm just assuming without loss of generality, basically, you can just say that B1 is at the center. It doesn't really matter which one you choose right now. We can always reorder them at the end. Switch A1, B1, do whatever we need to do. So if B1 is here, then the B2 can be some here, or B2 can be here maybe. But if B2 is here, then C1, C2 will have to both be here. And that won't work since they're next to each other. And then the other case is that if B2 is on the other side, C1, C2 will have to be here. And that also won't work. So none of these cases will work. None of these cases do work. This case doesn't work since if A1 and A2 are on both sides and B1 is in the middle, then C1, C2 will be forced to be next to each other. So the only case ends up being is a top case. And now let me explain how many values there are actually in this case. So in this case, let's see. So as you see in this case right here, in the first top row, we can rearrange it at the end. So let's just assume A1, B1, C1 at the top in this manner. Then A1 cannot go here because then A2 cannot go here because if A2 is here, then A1 and A2 are now in the same column. What about if A2 is here? If A2 is here, well then where can B2 go? So if A2 is in the very center position, then B2 can go here. But then if B2 goes here, then C2 will be forced to go here. And that doesn't work because C1 and C2 are now in the same column. So that means B2 will have to go here. So that C2 can go here. Because now that C2 is here, now we see that all of them are not in the same column. So that's one case that does work. If A2 is at the very center position. So that's just one way that does work. And another way that works is if A2 is at the third position. So if A2 is right here, then B1 has to go here. B2 has to go here because B2 cannot go in this position, since that would mean B1 and B2 in the same row. And that's not allowed by our problem statement. And that would force C2 to go here, and we see that does work. Since the A's, the B's, and the C's are all in different columns. All in different columns and rows. So this is another case. So a total of two cases. Of course, like I said earlier, we're going to have to multiply by some numbers. So you have to do 2 times, we can rearrange these three positions in 3 factorial ways. Because we have A1, B1, C1. We can rearrange them in 3 factorial ways by the factorial formula. And then after that, we can also multiply by 2 to the 3 because we can switch A1, A2, we can switch B1 and B2, and we can switch C1 and C2. So instead of having A1 in the top and A2 at the bottom, we can have A2 at the top and A1 at the bottom. So we multiply by 2 cubed to flip the A's, B's, and C's. So the answer is just 2 times 6 times 8, which will be 96. And that's the solution for this problem. Another somewhat bashy casework way that I did was that I just said assume A1 is here, just to give you another perspective on how other methods could work. I'm not going to go into the full-fledged solutions, but I'm just going to quickly outline the key steps. Basically, if A1 is here, we have the different cases for where A2 can go. So A2 can either go here, here, or here, and then you can just bash out all these cases and you'll get 96 as well. Except I think this method takes a little bit longer. So I think the solution I presented was a lot nicer and cleaner. To summarize the key ideas, what we did is we realized that we can either have the different rows tricks. We realized that the different rows, that the A's will have to be in different rows, the B's will have to be in different rows, other than in the small case. But we see that doesn't work. This case here, we see it doesn't work. So we know that we can just rearrange in this case and we get 96 from there. So I think this is a really cool problem. Okay, so the reason it's 2 times 3 factorial times 3 to the 3. So basically we have 2 here, right? Because 2 ways to arrange it. We have A2 here or A2 here. And then from there, we assumed that A1, B1, and C1 were here in the first row. But then what we see is that A1, B1, and C1 are in the first row. There's 3 factorial ways to rearrange A1, B1, and C1. Because we can also have something like B1, C1, A1. Because that also works, right? And then we can just switch like the C's, the B's, and everything else. So that's why we multiply by 3 factorial. But then again, we also have to multiply by 2 to the 3 because the reason we multiply by 2 to the 3 is we can switch the exponents. I don't know why the eraser's so big. So I can make A2 go here and A1 go here. Or I can do the original A1, A2 or A2 and A1. Similarly for B1, I can either have B2 on top and B2 on the bottom, or I can have the opposite. I can have the 2 on top and the 1 on the bottom. B2 on top and B1 on the bottom. So those are the different cases. That's why I multiply by 2 for the B's. I multiply by 2 for the A's because I can flip the A1, A2. And I can also flip C1 and C2. And I can also flip C1 and C2 and B1, B2 and A1 and A2. So then it's just going to be 2 times 3 factorial times 2 cubed. And that's just 2 times 6 times 8, or 96. And that's the answer for this problem. Okay, so hopefully that was clear now. If you're still confused, you can try rewatching the recording. Okay, now let's take a look at this problem. This is another cool problem. It's somewhat bashy problem, I should say. So, how many 3-digit numbers are composed of 3 distinct digits such that one is the average of the other 2? How can we do that? Well, I'll give you a hint. The idea here is we can split into 2 cases. Case 1, no zeros. No zeros whatsoever. No zeros. And then case 2, which I'll do here, probably. We do have zeros. So we have some zeros maybe in our digit. We have some zeros in our number. And then the idea here is that we can rearrange the certain cases. So I'll give you some time to try this out. Okay, so some of you thought I was muted. I was not muted. I was just writing out what I was going to explain. I was not talking earlier. I was just writing out the value so I can explain it now. While you were supposed to work on the problems. Sorry if you thought I was actually talking and trying to explain. Okay, so now let's continue for this problem. And I was just writing out the different cases so I could explain it now. Okay, so the idea here is what we can do is we can see that, okay, 3-digit numbers, what are the different cases? Again, we're having no zeros. So for this first case, and the reason I said I just put in the middle digit, so I'll account for arrangements at the end. So right now I'm just focusing on finding the number of combinations of 3 digits. And I'll range them, multiply by whatever I need to multiply at the end. So right now I'm just going to focus on the actual ways to range it. So for example, I'm only going to count, let's say I'm only going to count, for example, I'm only going to count through 2, 3, 1, 1 time right now. And I'll multiply the arrangements for these 2, 3, and 1 digits at the end. And I'm also just going to assume right now that the middle digit is the one that's the average of the other 2 digits. Okay. So the middle digit is the average of the other 2 digits. I'm just assuming that. Of course, we'll multiply for rearrangements later. Let's see here. So in this case, we have that the sum of the first and last digit has to be 1 times 2 or 2. Since we're assuming the middle digit is the average of the first and the third digit, which means it's going to be 2, 0 or 1, 1. But again, we're doing the no zero case. So 2, 0 won't work. And 1, 1, well, that won't work since 3 distinct digits. So this, we can just cross that out right off the bat. The next case is if you have a middle digit of 2, meaning the sum of the first and the third digits will be 2 times 2 and 4. So it's going to be 1 and 3, or 2 and 2, or 3 and 1. But again, I'm only counting for the number of distinct arrangements right now. I'll multiply at the end for them. So 1, 3, or 2, 2. And again, 2, 2 doesn't work because that would mean the digits are not all distinct. Right? So only case that works is 1, 2, 3, and of course rearrangements of that, which we'll account for later. Similarly, in this case, this means that the middle digit is 3, or the average digit is 3. The sum of the first and the third digit has to be 6. So 1, 5, 2, 4, or 3, 3. But again, 3, 3 doesn't work since that would mean we would have duplicate digits. And 4, 2, and 5, 1 will also work, but we're counting for arrangements at the end. And now I'm going to go a little bit faster to the remaining possibilities since I've already explained what I'm doing. So as you can see here, we have 1 and 7, 2 and 6, 3 and 5, or we can have 4 and 4. But that doesn't work since 4 and 4, that would create a number with all 3 digits equal. And now for this next case here, we can see that if 5 is in the middle, the sum of the first and the third digits has to be 10. And that would mean that we have 1 and 9, 2 and 8, 3 and 7, 4 and 6, or 5 and 5. If 5 and 5 doesn't work, since that would mean all 3 digits would be the same. So overall, we have those cases there. Now for 6, we would have, well, 6, if 6 in the middle, we could have 3 and 9. Since remember, no digit can be more than 9. So the idea here is that 3 and 9, as you can see here, no digit can be more than 9. So in order to get a sum of 12, both the digits have to be 9 or less. So we can have 3, 9, 4, 8, 5, 7, and then 6, 6. But 6, 6, 6 won't work since 6, 6, 6 has 3 digits the same, as I've already said. And I can continue on. For a sum of 14, we can have 5, 9, or 6, 8, or 7, 7, which won't work. For 8, we can have 7, 9, or 8, 8, which won't work since 8, 8 is duplicate digits. For 9, if the middle digit is 9, the sum of the first and the third digit is 18, meaning both digits have to be 9. But again, that doesn't work since that means duplicate digits. So overall, as you can see here, there's one case here, or let me make that in a more vibrant color. So, Okay, so as you can see here, let's say there's going to be one case that works here, one case that works here, two cases that work here, three that work here, four that work here, three that work here, two that work here, one that work here. And that's going to be a total of 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1, which is just going to be equal to 16. Oh, that's not the answer, sorry. I did the same mistake last time. That's not the answer. We have the other case still. And we have to also account for arrangements. So 16 is the sum of all the possibilities here, except like I said earlier, we can also arrange the digits. So for example, 5, 7, 8. 5, 7, 8 can be rearranged, for example, to 7, 8, 5. And that would also work. Since not necessarily the middle digit has to be the average. Or sorry, 5, 7, 8 doesn't even work. Sorry, something like maybe 5, 7, 9 can be rearranged to 9, 5, 7. And that would work. Since in this case, in the first case, we have 7 being the average of 5 and 9. In the second case, we have 7 being the average of 5 and 9. It does not necessarily have to be the middle digit. And we can also rearrange them in ways that we haven't counted for yet. So overall, we can rearrange them in 3 factorial ways. So 16 times 3 factorial is 96. And then as you can see here, we're done with the first case. And not the answer. We still have the second case. I keep boxing the answer before I finish the whole problem. Okay, so as you can see here, so the case 2 is when they have a 0 digit, then the different possibilities are 2, 1, 0 if the middle digit is 1, or we can have 4, 2, 0 if the middle digit is 2, or we can have 6, 3, 0 if the middle digit is 3, or 8, 4, 0 if the middle digit is 4. So these are the cases with a 0 in them. Of course, multiplying arrangements at the end. So these are the 4 cases that have zeros in them. Okay, so now from here, from these 4 cases that we have, we can see that 0, these are cases that all have 0. And the reason that they all work is because if this is 1, then we can have 2 and 0, since the sum of those 2 digits has to be 2. If it's 2, then we can have 4 and 0, since the sum has to be 4. If it is 3, then we can have 6 and 0, since the sum has to be 6. If it's 4, it can be 8 and 0, since the sum has to be 8. So overall, we have 4 different cases here. But again, we have to multiply by rearrangements. So for example, for 210, we have the different, we can rearrange them as 201, 210, 102, 120. So overall 4 rearrangements of 210. Because remember, the reason it's not just going to be 6 rearrangements is because 0 cannot be the start of the number. So the arrangement 0, 1, 2, for example, would not work. Because that's not a 3-digit number. How many 3-digit numbers? That would be a 2-digit number then. So we only have 4 rearrangements that are 3-digit numbers that don't start in a 0. So it equals 16. So overall, we have 96 plus 16, which is 112, which should be the answer for this problem. And this is a pretty good casework problem because if you try to do it without the reason I separated into 0 and no 0 is because with 0 we run into some complications of now there's only 4 ways of rearranging the number. So that's why I thought, okay, so for each of these numbers, there's going to be 6 ways of rearranging them. But the ones that have 0 in them, there's only going to be 4 ways of rearranging them. So it's going to probably be easier to deal with them separately because I don't have to worry about, now I have to worry about, 0 in the beginning, or those cases. So better to just deal with them separately and count them individually and then sum them up. And then we just take different cases for 1 through 9. And you might be wondering the reason I wrote it in this weird fashion is because these 2 cases are both the same. These 2 cases are both the same. These cases are both the same. And these cases are both the same. So I was just trying to show the pattern of how each of those cases will be like symmetric around 5. Okay, so now as you can see here, we have another problem from last year's AMC 10. So if 10 people standing around a circle, exactly 3 of the other 9 people. And the 2 people standing next to each other. And we were asked to find how many ways for the 10 people to split up into 5 pairs. So basically, the 2 people standing next to the people around them, and then the other on the opposite person as well. Those are the 3 different cases there. Okay, so I'm going to let me draw a circle. So try to work on this problem for a few minutes. In the meantime, while I try to draw a good diagram. Because now let's go to the solution of this problem. This problem is basically just doing casework. And you basically just do casework on the number of pairs. The way I'm going to explain it is casework on the number of opposite pairs that there is. So basically the different possible pairs are, well, we can either have, let's say, so let's just take different cases. Case 1, let's say, is 0 opposite pairs. So 0 opposite pairs. So all the pairs are people who are next to each other. So what are the different cases for that? Well, 1 and 2 can be a pair, 3 and 4 can be a pair, 5 and 6 can be a pair, 7 and 8 can be a pair, and 9 and 10 can be a pair. So that's one case. So that's 1. And the other cases we can have 2 and 3. Let me just erase this. The other cases that we can have 2 and 3 be a pair, 4 and 5 be a pair, 6 and 7 be a pair, 8 and 9 be a pair, 10 and 1 be a pair. So really we have 1 plus 1 equals 2 cases for this. Case 2 is 1 opposite pair. So for this case, we have, so if we have 1 opposite pair, then let's just say that our opposite pair is 1 and 6. Let's say that 1 and 6 are a pair for people who know each other who are opposite from each other. Then there's only one way to pair people up from the remaining people. So let's say, well, there's 1 opposite pair, and then all the other 8 people are pairs from people who are next to them. So then the only case is that if 1 and 6 are an opposite pair, then we can have, let's say, 2 and 3 be a pair, 4 and 5 be a pair, 7 and 8 be a pair, and 9 and 10 be a pair. And that's only one case. And the reason that something like maybe 3 and 4, for example, can't be a pair, because if 3 and 4 is a pair, now we have 2 is not a pair with anybody else. So that won't work. So that means there's only going to be one way for this case. And for this third case here, let's say we have 2 opposite pairs. Okay, so we have 2 opposite pairs. Let's say we have, for example, 1 and 6, and then we have 2 and 7. Then what? Well, then we can see from here is that if you have 2 opposite pairs, then 3, 4, and 5 are left. We're left with only 3 people in each group. So left with 3 people here. Or let me not do that with the pen. Then we're left with 3 people here and 3 people here. So we have 3 people on both sides, and 3 people. We cannot divide 3 people into evenly divided pairs, so that won't work. So there's going to be 0 ways for this case. But then also, even if we, let's say, space out our opposite pairs, so we make another opposite pair like this, for example, this also won't work. Because now these 2 people can form a pair, these 2 people can form a pair, but now these two people are left alone. So there's 0 cases in this case. Case 4 is 3 opposite pairs. So if you have 3 opposite pairs, let's say add another pair like this. So as you can see here, for this case, for case 4, there's only going to be 5 different ways. The reason there's going to be 5 different ways is because you can imagine that we have these 3 pairs here, and so the middle pair from 2 to 7 right now, we can imagine that there's 5 different possible middle pairs. So we can either have 2 and 7 be the middle pair. So there's 3 pairs, right? And I'm talking about the ones that are consecutive. So we can either have the 2 and 7. Let's count how many middle pairs there are. So, for example, 2 and 7 can be a middle pair. So 1 and 6 can be a middle pair, the middle pair. 2 and 7 can be the middle pair like we see right now. So 2 and 7 can be the middle pair like I have right now. Or we can have 3 and 8 be the middle pair. Or we can have 4 and 9 be the middle pair. Or we can have 5 and 10 be the middle pair. And then, of course, the other 2 opposite pairs will be around those 2 pairs. And that's going to be a total of 5 cases in that total of 5 cases, because there's 5 opposite possible middle pairs. And then also, we can also imagine putting one space in between. So we can put it here like that. But now we're just left with four different people that have no pair. Like people who are next to a pair. Of course, we can have opposite pairs, but this is the case with only 3 pairs. So there's we cannot have people next to each other in a pair anymore. And now the 5th case is we have 4 pairs, opposite pairs. But if we try 4 opposite pairs, we'll see that if we have 4 opposite pairs, you can have something like this, for example. Oops. You have something like this, for example. Now we're just left with 2 people who are not part of any pair. So that's 0 cases. Let me just circle them all out so it's clear. 0. This was 5. I don't know, it got erased, I think. In the final case, case 6, is 5 opposite pairs, or all the pairs are everyone's in opposite pairs, and that's just going to be 1 case. Because again, there's only one way to have this. So that's 1. We add all these up, we get 2 plus 5 plus 5 plus 1, which is 13. Which is the answer for this problem. Let me box that. Okay, so now let's briefly review complementary counting. This is a pretty basic concept. Basically, we just subtract what we don't want. And there's a quick example. How many positive integers have at least 1 digit? That is a 2 or 3. This is just going to be how many total 4-digit numbers are there. How many total 4-digit numbers are there? Well, this first slot can be 1 through 9, so 9 choices. Second slot can be 0 to 9, so 10 choices. Third slot and fourth slot, also 0 choices. So total 9,000 4-digit numbers, and we can just not have a 2 or 3 in any of these slots. So 7 times 8, because if you don't have a 2 or 3, so in this first slot, we can either have 1 through 9, besides 2 and 3, so 7. In the second slot, we can have 0 through 9, besides 2 and 3, so 8. And then this slot can also be 8 and 8, for a total of, I believe, 3, 5, 8, 4. So the answer should just be 5, 4, 1, 6. And remember, from the AMC class, we discussed a lot more of these types of problems, but this is a quick review. At least means we use complementary counting. Let's move on to some more challenging problems now. So 2 tour guides lead 6 tour lists. The guides type split up. Each tourist must choose one of the guides with the stipulation of each guide must take at least 1 tourist. How many different groupings or guides or tourists are possible? Okay, so the idea here is how many different groupings? So the idea here is that we have 6 tourists and each tourist must choose one of the guides. So basically, each of these tour guides so we have 6 tourists and 2 tour guides. So each of the 6 tourists have 2 choices. They can either go to the first tour guide or the second tour guide. Okay, so we can go we have 2 choices. You can either have tour guide 1 or tour guide 2 with each of the 6 tourists. So 2 choices for each of the 6 tourists. So 2 to the 6. But we're overcounting. Remember, at least, which means you use complementary counting. This technique even applies for 8 to 10 level problems. So then we subtract 1 and 1 because we subtract the cases where all the tour guides are given to all the tourists are given to one tour guide. So we just do minus 2. For the cases where all of the tourists are given to one tour guide 1, or all the tourists are given to tour guide 2. So if T1 has 6 people and T2 has 0 people, or T1 has 0 people and T2 has 6 people. And I believe the 2020 AMC 8 also had a similar problem, but slightly harder than this. This is just 62, the answer. Okay, so now let's take a look at combinations. Again, review of these basic formulas that we learned. Now let's look at some basic problems. At the gathering of 30 people, there are 20 people who all know each other and 10 people who know no one. People who know each other hug, and people who do not know each other shake hands. And we got to find how many handshakes occur. Okay, so how can we do this? Well, firstly, we should note that out of the 30 people, we can think of them as two different groups. So 20 people. The 20 people who all know each other, so know each other. And they can think about another group of 10 people who don't know each other or anyone else. So these two groups you can think of them as. So now, as you can see here, from here what we can see is that the 20 people who do know each other, from those people, they can each shake hands with a person from the people who don't know each other. So it's going to be 20 times 10, or 200. Because each person doesn't know each of those 20 people who know each other can shake hands with each of the 10 people who don't know each other. Okay, so that's 200 ways for that. Another way is that if we have 10 people who don't know each other, each of them shakes hands with each other. So we can add 10 choose Q equals 45 ways. 45 ways for the 10 people who don't know each other. They can each shake hands. So each pair of the 10 people who don't know each other shake hands with each other. So we add 45 handshakes for a total of 200 plus 45, or 245 handshakes. And as you can see here, the idea for this problem is that we just look at the choosing. And an alternative way of doing this is that we see that out of the 30 people, for all the 10 people who don't know anybody, they each shake hands with and the reason is basically for this first case is 20 people who know each other will each shake hands with people who don't know each other. Because the people who don't know each other don't know the 20 people who each know each other inside the group. So inside the group we have 22 hugs here, but these are not handshakes, so we're not going to count them. So we have 245 handshakes total. Another way that you can do is for each of the 10 people who know no one, they each shake hands with 29 people. And for the 20 people who know each other, they can shake hands with the 10 people. But then each handshake is overcounted twice because we can take 2 people. When the 2 people handshake, we're overcounting them. So we divide by 2 because we're counting the handshakes that each of the people does. So for example, if person A handshakes person B, we're counting it as a person A handshakes and a person B handshakes, when really just one handshake. So we divide by 2, and this also simplifies to 245. Okay, so now let's do our raffle. Thanks to our sponsors, we're going to be raffling a Brilliant Premium subscription and a Wolfram Notebook subscription. Thanks to our sponsors, Daily Challenge, AOPS, Brilliant, and Wolfram. So you can fill out the raffle form with the link. And again, the Brilliant subscription is only for people who attempt the homework. And by attempting the homework, you don't necessarily have to solve all the problems or even one of the problems. Just that you have to give your thoughts or ideas on, or at least try the problems. And then you have to post it. And also, while you guys are waiting in the break, you can try this problem. This is a really clever problem, and it seems very hard, but it has a really nice solution. So I definitely like this problem. This is again a really clever problem, so I encourage you all to try it while you're in break, or you can take a break too. And choose whichever one you want to do. And I'm not actually talking right now. I will just be making some notes on the screen right now. Okay, now let's begin. This is actually a really clever problem, so I think this is one of the best problems in this class today. So out of the first 5 letters, we cannot have any A's in the first, no B's in the next 5 letters, and no C's in the last 5 letters. So then we can see that the first 5 letters has to be only B's and C's. So only B's and C's. So we don't know how many B's or how many C's, but all we know is that no A's can be the first 5 letters, so it has to be only B's or C's. So let's just say that we have K B's and 5 minus K C's in the first 5 letters. Okay? Now, in the next 5 letters, let's say we have, so next 5 letters, there can be no A's here, no B's, and no C's. So there can be no A's in the first 5 letters, no B's in the next 5, and no C's in the last 5. That means that the middle 5 letters has to be only A's and C's. And since there are 5 minus K C's here, and there's no C's here, the remaining K C's, since we have 5 C's, has to be in the middle section. And the remaining 5 minus K A and 5 minus K A's will have to be in this middle section, for a total of 5 letters in this middle section. Because a total of 5 letters has to be in this middle section, and there has to be K C's in this middle section as well, because there's 5 minus K C's in the first section, and there can be no C's in the last section. And since there's K C's in the middle section, for a total of 5 letters in the middle section, there has to be 5 minus K A's here, meaning there has to be K A's in this last section, and there also has to be 5 minus K B's in this last section, in order to get a total of 5 A's, 5 B's, 5 C's, and 5 letters in each of these 3 slots. So now, that was a hint to this problem. So now try continuing and solving it from here. And I think this is a really nice solution, so it will be great. And this has like I was saying earlier, this is a very nice solution. So now let me just show you what the solution actually is. So as you can see here, there's KB's and 5 minus KC's in the first slot. So in this first slot, we have 5 letters, and out of these 5 letters, we have to choose K of them to be B's. So it's just going to be 5, choose K. And in this second slot here, we have 5 letters, and we have to choose K of them to be C's. So times 5, choose K. So in the final slot, again, we have K A's, so we must choose, out of the 5 slots, to choose K of them to be A's, so times 5, choose K. For a total of 5, choose K cubed. That gives us a lot of good information. Okay, so now what? Well, now what do we know? Firstly, we see that 5 choose K cubed is a total number of ways of doing so. But the idea here is that K can be different values. K can be anything from 0 to 5. So the total number of ways of arranging it is just going to be 5 choose 0 cubed, plus 5 choose 1 cubed, plus 5 choose 2 cubed, all the way till 5 choose 5 cubed. And that can be written as a summation of K equals 0 to 5 of 5 choose K cubed, which is option choice A. And to summarize, this was a really nice solution. Basically, rather than doing a bunch of casework that would take forever, I'm just saying, let's say that there's KB's, and let's assume there's KB's and 5 minus KC's. We'll worry about the different cases for K as we go. And we can say that there's KC's and 5 minus KA's, KA's and 5 minus KB's in the beginning. So overall, we can just do 5 choose K cubed of arranging each of the 3 slots. And then we sum of it all from K equals 0 to 5. Because we can either have 0 to 5 of the letters. And I think this is a really nice solution. So I think it's great to know that there's such nice solutions exist to this problem. So somebody was asking, how do you think of this? Well, how you think of this is you would notice that there's no A's in the beginning, as stated by the problem. So if there's no A's, there has to be B's and C's. Okay, so if the first 5 letters have B's and C's, the first 5 letters have to be B's and C's. Then the next, we also have that the middle 5 letters will have to be C's and A's. And the last 5 letters have to be A's and B's. So we can assume there's K and 5 minus K here. And then we see that from there there's going to be KC's in this next section, 5 minus KA's in this next section, KA's in this next section, and 5 minus KB's in this next section. So overall, we just have 5 minus K cubes, and we sum them all. So yeah, definitely is a very nice solution. Another way that would be take a long time is just brute forcing it. We can also take a look at stars and bars. So again, we already covered this formula in the AMC math counts class, and we covered that there's going to be K minus 1 bars between the n objects. So let's look at some problems. Let's start off with the very simple stars and bars problems. We have 6 cookies. And then we have chocolate chip, oatmeal, and peanut butter cookies. And there are at least 6 of each kinds of cookies. So that means because there are at least 6 of cookies, we won't have to worry about running out of cookies. Because if there was, let's say, let's say peanut butter cookies, well, only 5 peanut butter cookies, then we cannot have all 6 peanut butter cookies. But we're given here at least 6 of each of the kinds of cookies, meaning that we can have any combination. We can have all 6 peanut butter cookies if we wanted, all 6 chocolate chip if we wanted, or all 6 oatmeal if we wanted. We have enough supply if we did the cookies. Okay, so now what? Well, now we can see that. Let's just divide it. Let's place 2 bars here and here. Or it doesn't really matter where we place the bars, but it's just going to be here. This first area is going to be chocolate chip cookies, chocolate chip. This region here, let's say these are all going to be oatmeal cookies. And let's see the region here, let's say they're all peanut butter cookies. So as you can see, the 2 bars split the 6 cookies into 3 kind of groups of each of those cookies. Chocolate chip, oatmeal, and peanut butter. So therefore, the number of ways of placing 2 bars and 6 cookies is the same as dividing the 6 cookies into 3 different types of cookies. So it's just going to be equal to 2 bars, 6 cookies, so 8 choose 2 equals 28. So this is the answer. Okay, now let's take a problem from the Omega Learn Math competition. So this is a problem that I wrote for the Omega Learn Math competition. Basically, the intuitive reasoning that most people think of is just doing casework, but it has a nice stars and bars solution. So you can also check out the video for all the solutions to the Omega Learn Math problems on this channel. So you can check out the video with problems similar to this. Okay, so we have 3 squirrels and 19 identical acorns. The first squirrel has a positive odd number of acorns, and second squirrel has a non-negative even number of acorns. The third squirrel has an even number of acorns greater than or equal to 4. How many different ways can you distribute the acorns? So basically, the first squirrel has a positive odd number, so it can be represented in the form 2a plus 1. The second squirrel is found with any non-negative even, so it's going to be of the form 2b, let's say. And this last one is going to be 2c plus 4, whereas a, b, and c can be 0 or more. Because positive odd means it can be 1, 3, 5, 7, etc. So it can be expressed in the form 2a plus 1. Non-negative even is just 2 times some number that's 0 or more. And 4 or more that's even is just 2c plus 4. And then we have that 2a plus 1 plus 2b plus 2c plus 4 is 19. And then that means that 2a plus 2b plus 2c is 14. Or a plus b plus c is 7. Okay, so now we can use stars and bars to distribute this out. And in general, we want to use stars and bars whenever you have identical items and you want to distribute it into distinct groups. So in this case, we have identical, you can think of it as 7 ones, kind of. And you want to distribute it to 3 groups, A, B, and C. So you can give like 4 to A, 2 to B, and 1 to C, for example. So whenever you want to use stars and bars, whenever you have identical items, so maybe like balls, that are all the same in 3 groups. So maybe like 3 per people who want to divide the balls amongst. So that's when you want to use stars and bars. But like earlier problem, there's actually an early problem that we were distributing 6 different tourists to 2 different tour guides. So in that case, you cannot use stars and bars because the tourists are all different and not identical. So overall, we have a plus b plus c is 7. So we can just have 2 bars and 7. You can think of as 7 dots. 3, 4, 5, 6, 7. That's just going to be equal to 9 choose 2, which is 36, the answer. Yeah, and this one, the key idea, it was a really clever application of stars and bars. And another way to do it is just casework, but I'm not going to show that because it's way longer. So now there's also combinatorics for geo problems. So we have that the sum number of squares from 1 to n is just going to be 1 squared plus 2 squared till n squared, and it can be represented in the like that. And we also have other formulas for rectangles and ways to get from 0, 0 to xy. So let's explore this problem right here. So the idea for this problem is that we have how many squares contain this black center square. So for this problem, the idea here is we can just do casework. So if it's just a 1 by 1 square, or that's not a very good color to use. Let's just make that a little bit thicker so I can draw it a little bit better. Well, let me just use, so for the 1 by 1 squares, there's only going to be one way. Now for the 2 by 2 squares, we can have this, for example. We can have this, or this. So we have 4 different possible 2 by 2 squares. And then we also have 3 by 3 squares. So 3 by 3 squares, for example, the idea here is that for 3 by 3 squares, we can think of it as 1, I'm not sure what to use to make it more clear and visible, or let me use a different colors just to make it blend out a little bit. 2 and 3 in this row. So we have 3 different possible squares in this row. And similarly, we can also have squares in the next row. So we can have squares like this, like this, or like, so that's another possibility there. And then we can also have squares above it. So we can have, for example, something this square, or this square. I don't know why it keeps doing that text box, or this square. So we have a total of 9 squares. And another more intuitive way of doing that, maybe, is just to say that the 3 by 3 squares, we can think of it as 3 possible dimensions. So we can think of it as 1, 2, 3 possible vertical sides. And then we can also think of it as 3 possible horizontal sides. So this, or this. So it's going to be plus 9. And both ways work fine. Whichever one you find more intuitive to understand, go ahead and use that way. And we can also have, for example, 4 by 4 squares. We can have 4 by 4 squares. We have, for example, this square, this square, this square, this square. And something you can also notice is that all 3 by 3, 4 by 4, and 5 by 5 squares contain the black square. So we don't even have to worry about that. So I made it a little bit unnecessary. So we can just think of it as 3 by 3 squares. It's just, you can think of it as 1, 2, 3 choices, and then 1, 2, 3 choices here. And then for 4 by 4 squares, you can think of it as 2 choices for each dimension. If that's clear. Or you can also think of it either way, whichever one you find more intuitive and clear. You can go with that. For a total of 19. Okay, so now let's take a look at our next problem. And this problem we already covered in the previous class. But let me just show you a quick alternative way of doing it, because I think some of you find it confusing. I actually noticed there's a maybe more intuitive way to understand the solution to this one. So we have 25 choices for the square for the first block, right? So let's say we choose our first block here. And if we choose our first block here, then we can no longer choose any of these squares. Because if you choose the first if we choose our first block, the blue block I marked, there's 25 choices for it, because there's 5 by 5, 25. All the other squares couldn't there. And then similarly, we can also choose now how many ways are there to choose another square? Well, there's one square that's already occupied, and there's if you count it out, there's 8 squares that got x'd out. So we put an x on 8 squares, and 1 square we used. So we're left with just 25 minus 9, or 16 choices for the second square. Maybe like here, for example. And then if we put it here, we put an x, 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 x. And now we're just left with, you can count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 choices. So we just do times 9. But then, we also have to divide by 3 factorial, because it doesn't matter what order these 3 squares are in. We can choose another square here, for example. The pink, blue, and green square can be rearranged in 3 factorial ways, so we divide by that. To get that is equal to 400 times 9 by 6, which is 600. The answer, which you got earlier using the other method. You can check out the AMC math counts class for the other method. Okay, so this is our last problem for today. We have a regular tetrahedron, and 2 colorings are indistinguishable if it can be rotated. So rotations don't matter. How many distinguishable colorings are possible is what we want to find. So let me just draw a tetrahedron really quickly. So let's color the bottom face to be blue, for example. So there's just going to be a few cases here. The first case is all 4 sides of the tetrahedron. Remember, the tetrahedron has a bottom face and the 3 side faces. So the first case is all 4 sides are the same color. Let me just copy this really quickly so I can not have to read out the tetrahedron. The first case is all of them are the same color. So let's say all the faces are blue. That's going to be one way. But then there's going to be 3 colors, red, white, or blue. So we have 3 different choices if all faces are the same color. Now, what about if we have almost all the faces be the same color? So let me just paste. So now what if one face is a different color, but all the other faces are the one color? So let's say this face is blue, also blue. The bottom face is also blue. But then we have that this face is maybe red. This face right here is red. That's going to be another case. You can imagine the bottom face being one color and the 3 side faces being another color. So then as you can see here, there's going to be 3 choices for the first color that you use. So like 3 choices for the bottom face, the face that appears only one time. So the red face, for example, in this case. And then 2 choices for the blue, basically for all the other side faces, because we have 2 colors left. And this gives us 6. And remember, it doesn't matter whether we have the red face on the bottom or on the side, because rotations don't matter. Another case is that, let me paste it again. We have 2 and 2. So we have 2 faces one color and 2 faces the other color. So maybe you have 2 blue and 2 red faces. So then there's just going to be 3 times 2 ways, 3 ways to select the first color that will appear in 2 faces, and 2 ways to select the second color that will appear in 2 faces, divided by 2, because we can flip. It doesn't matter whether we have red on 2 faces, red and blue, or blue and red. Because in this case, we have 2 faces red and 2 faces blue. It's the same as having 2 faces red and 2 faces blue and 2 faces red. But on the other hand, in this case, having 3 faces blue and 1 face is red is different from having 3 red faces and 1 blue face. So that's why I did not divide in this case, but I have to divide in this case. And in the final case is that we have the final case is if you have 2, 2, 2, and 1. So we have, let's say, 2, 1, 1. So we have two faces that are one color, 1 face that's another color, and 1 face that's another color. And then let's just say that two faces are blue, and then one of the faces is red, and one of the faces we just leave to be white. Oops. I don't know why that got erased. And one of the faces, two blue faces, one red and one white face. Let's assume that. Well, then we have four choices for the first color. I'm sorry, not four. Three choices for the first color. Two choices for the second color. And then one choice for the third color. Divided by 2. The reason is the red face and the white face, the two colors that appear only one time. It doesn't matter whether we have one red face, one white face, or one white face, one red face. Because we can imagine flipping the white face and the red face. It doesn't matter whether we have red face, white face, or white face, red face. Which is 3. And this is also 3. This is 6. So we add them up, we get 3 plus 6 plus 3 plus 3 is 15. And that's the answer for this problem. So there's also this problem here from the 2020 AMC 10, but we didn't have time today. So it will be in the homework. It will be in the homework for this class. And this problem actually is really a nice application of stars and bars. Thank you for attending this class. And I hope you all try the homework problems as well. And they'll be emailed out to you all. Thank you for coming to this class. See you all. And remember, next week we have no class. Or our next class will be 2 weeks from now. You can check the Omega Learn website for the schedule. And now you have more time to work on the homework problems. You have 2 weeks now.